So now let's discuss about the remaining part of the centrifugation chapter. So first of all, we are talking about the outcomes that we have drawn from the sedimentation principle. Okay, so the first outcome is the sedimentation velocity is proportional to the mass. Okay, mass of the particles. So here another important thing that I need to mention, that density play here a important role. What kind of important role? So remember that a denser particle will exhibit a lower buoyancy force than the less dense one. Okay, that means that density is inversely proportional to the buoyancy in case of your centrifugation principle, that you need to keep in your mind. Another one is shape. Compact particle will exhibit less frictional coefficient than a extended particle. Okay, that means if your mixture have protein and DNA, then protein will sediment faster than the DNA, because DNA is relatively extended. Okay, so it will exhibit a greater viscous drag and a greater frictional coefficient than the protein. Okay, and it is proportional to the density of the solution. Okay, not only density, it is proportional to the our product of v bar rho. Okay, so if v bar rho is less than 1, then particle will sink, and if v bar rho is greater than 1, then particle will float. You can simply remember this in such a way that v bar is what? V bar is the volume of the each gram of particle that is occupied. Each v bar is the volume of the each gram of the solute that is present in the solvent, right? That means it is occupied a portion of the solvent, so that will in turn affect the buoyancy force. So buoyancy force will help in floating. So if v bar is high amount, then it will, your particle will float, and if v bar is less amount, then your particle will sink. That is the idea. So now let's move to the next topic. So we have touched about preparative and analytical centrifugation. In preparative centrifugation, we are isolating a particle from the mixture. In analytical centrifugation, we can analyze. In fixed angle rotor, we are holding our tube at 45 degree centigrade. Again 45 degree angle, and here faster separation is confirmed, but fixed angle rotor cannot ensure the movement of all the particles at the bottom, because here the direction of the force is at opposite direction to the direction of the particles. And in case of swinging bucket rotor, we have taken our tube horizontally at 90 degree angle. Okay, although it cannot provide that much faster separation that fixed angle can, but it can accomplish all the movement of all type of particles. So swinging bucket rotor can ensure that yes, all the particles are separating, all the particle can be separated, or all the particles movement towards the bottom. Okay, that our fixed angle rotor cannot, because in swinging bucket rotor, the direction or the position of the particle is exactly at the direction of the force. Okay, or the path of the force. Then we have discussed about the RCF, that is our small r omega square by g, and in omega we can replace omega with 2 pi rpm 60, and in case of g can be replaced by 980. Okay, that can ultimately give us the relation between RCF and RPM. That is very important. Then we have discussed about the sedimentation coefficient, that is S, that is V by omega square R. Okay, now another topic, that is differential centrifugation. Although we have discussed about differential centrifugation in earlier times, but let's revise it again. So I will use these diagrams. I have taken it from microbiology notes. You can easily search about microbiology notes in Google. So let's start the discussion. So I will use this diagram instead. Okay. So the sample to be separated will be mixed with the solvent uniformly, a uniform mixture, as you can see here. The idea is, in differential centrifugation we are using the difference in their sedimentation rate for the separation, okay, that in turn ensure separation on the basis of their size and density. Okay, how? Let's see. First of all, by after taking the sample in the centrifuge tube, we will run the centrifuge tube at the lowest speed that will ensure the pillating of the largest and the highest sedimentation rate containing particle. Okay, as you can see, the green particles are pillated. Okay, then we will decant the supernatant. Okay, and we will again run the new centrifuge tube that contain only the supernatant. Okay, but this time we will increase the centrifugal field or centrifugal force by just increasing the speed, and we will also increase the centrifugation time, okay, to pillate the next highest sedimentation rate containing particle. Okay, then we will again decant our supernatant and we will again perform the next round of centrifugation. Okay, that is how the sedimentation is accomplished, and you need to remember that in each subsequent step you have to increase your speed, that is the centrifugal speed, that will increase the centrifugal force for you. And also you have to increase another important thing that I want to mention, that is the centrifugation time, that will separate the next higher molecular weight containing and higher sedimentation rate containing molecule for you. And that's how, depending on the differences in sedimentation rate, differential centrifugation can separate particles. Okay, that term differential is used because here we are performing different centrifugation to separate each of the particles based on their differences in sedimentation rate. So that is the concept behind differential centrifugation. An example of thing where we are using differential centrifugation is the subcellular component separation. That is the very important thing. Okay, so now we have discussed preparative centrifugation, where we are isolating our desired particle from the mixture. Analytical centrifugation, where we are analyzing each of the particle. Fixed angle rotor, where we are holding the tube at 45-degree angle. Okay, and here the fixed angle can separate molecule at a faster rate, but it cannot ensure whether all the molecules is at the bottom of the tube or not, because here there is no force applied, because the direction of the force is exactly opposite to the direction of the particles. Okay, so now swinging bucket rotor, here the tube will be at 90-degree angle as the swinging bucket rotor swings and the process starts. Okay, that is why here we have provided a rack to suspend the tube so that it can move itself to acquire the horizontal position. That is important. Okay, and in that way the position of the particle become at the direction of the force. As a result, here we can ensure that yes, all the particles will be sedimented at the bottom due to the centrifugal force. Okay, then RCF, R omega square by G, where omega is 2 pi rpm by 60 rad per second, and then in G we will replace G with 980. Sedimentation coefficient V by omega square R we have discussed, and then we have discussed about differential centrifugation. Now let's talk about another thing, that is density gradient centrifugation. Okay, I will use this diagram to explain you the concept of density gradient centrifugation. So density gradient centrifugation is nothing new, it is just a modification of the differential centrifugation. So in differential centrifugation, the particles to be separated is in uniform mixture with the solvent. Okay, but in case of density gradient centrifugation, the particles are separated by a column. That column have a gradient of density. Okay, that means the amount of solute is increasing from the top to bottom, and that ultimately facilitates increase in density. Okay, so here will be a density gradient from the top to bottom, meaning that at the lowest density will be at the top and highest density will be at the bottom, and the medial area will exhibit intermediate density. Okay, that is the density gradient centrifugation if you are using such kind of matrix for centrifugation. Okay. Okay, now the question is, what is the utility of using such kind of thing? So density gradient centrifugation can help you to separate molecules in distinct layer or band. As you can see here, granulocyte, erythrocyte are separated at one band, ficol is separated and another one, mononuclear cells is in that band and plasma is that band. You cannot get such kind of environment in differential centrifugation, right? Because before separation all the mixture are uniform, right? But such kind of environment where all the separation before the isolation are already separated at distinct band, you can get only in case of density gradient centrifugation. And another thing I want to mention here, that here the suppose in case of plasma, the local density of the solvent is exactly equal to the density of the plasma. Okay, that is the idea, that is kind of the concept we have learned in case of isoelectric focusing, where protein when reaches a area where the pH of the environment matches its pI, the protein stops. That is how here, if the molecules find any environment where its density is exactly equal to the density of the solvent, it will stop. That is the idea of the density gradient centrifugation. Now we will divide density gradient centrifugation into two parts. Okay, density gradient centrifugation, I am mentioning density gradient centrifugation at DC. So it have two parts, one is RZC, meaning red zonal centrifugation, another one is your IC, that means isopicnic centrifugation. Okay, although we have learnt about isopicnic centrifugation in our earlier videos, so today we are also going to revise about isopicnic centrifugation. So now let's discuss about red zonal centrifugation first. Okay, so I have told you about the gradient. So now I want to mention you that matrix forming substrates that we are choosing for producing the gradient in the column will produce the gradient before centrifugation in case of red zonal centrifugation. Okay, that means the red zonal centrifugation will have the gradient before centrifugation. Okay, and now on the basis of those gradient, depending on their size and density, here two properties can play role, that is their size and density, they will separated. Okay, when they will get some environment where their density will match with the environment density, the particle will stop, leads to the formation of distinct layer or band. Okay, each of the band consists of different particles. okay, and that particles have same density and or same size. That is the concept of red zonal centrifugation. Okay, so red zonal centrifugation, the first goal of red zonal centrifugation is to prepare the media. Okay, so the media will be prepared in different concentration. So first of all we will prepare a concentrated solution, then we will simultaneously dilute it to get our required concentrations. Okay. So when we will add those matrix forming substrates in the tube, it will construct for you a density gradient that is from the top to bottom. Okay, that means in the bottom it will have the highest density and in the topmost layer it will have the lowest density. Okay, so here I want to explain you the three important precautions that you need to keep in your mind, that when you are adding a high concentration medium, you have to put your pipette up to the bottom of the tube or up to the bottom of the column. Okay, when adding high medium concentration, tip of the pipette should be placed at the bottom of the column, because so that we can done our job without disturbing the interface between layers. Okay, and another important thing, the prepared gradient should be used as possible as to avoid premature diffusion of the gradient layer. It is important thing. Okay, that means after preparation of the column we have to use it then and there to bypass the chance of premature diffusion of the gradient layers. Okay, and it is obvious, right? We have prepared a gradient, it cannot withstand for many time, we have to use it at the time, right? So three precaution very important for university purpose, that they can ask you what are the precaution you have to keep in your mind in case of red zonal centrifugation. Those are, when high concentration medium is added, the tip of the pipette should be placed at the bottom of the column. Okay, we have to use the gradient then and there, so that we can prevent the chance of premature diffusion of the gradient layer. Okay, another one is we have to avoid the disturbing of interface between the layers. Okay, now let's move to the next part, that is the centrifugation step. It is quite easy one, that is exactly what we have discussed in case of isopicnic. That is, after creating the column that have density gradient from the top to bottom, we will put a suspend of particle at the top of the solution in the column, then we will run the centrifuge, and now let's discuss what will happen. Okay, so this is our tube. Okay, in the tube up to that line, say this is our column. Okay, now we have placed a suspension of particles. Okay, now this suspension of particle will start migrating towards the downward. Okay, depending on, at different velocities depending on their sedimentation rate. Okay, that means what, their size and shape will play a great role. Okay, because on the basis of that the centrifugal force will acting differently on different particles, right? So and that is the difference between the isopicnic centrifugation and our red zonal centrifugation, because here we are separating the particle on the basis of size, but in case of isopicnic centrifugation bion density is used. Okay, so now in the complex mixtures, suppose it have a red particle, another one is black particle which is smaller one, the larger particle will move to the bottom of the tube, because the larger particles have greatest sedimentation rate that allow it to move through the greater density gradients, okay, to the bottom of the tube. But smaller black ball will have less mass that do not allow it to migrate too much at the bottom, so it will float at the top. That is the idea of the red zonal centrifugation, okay. That is, the larger particle will able to travel at the bottom of the layer because they are massive, right? That means they are larger in size simply, okay. And because the greatest mass allow this particle to travel through the layer with a greater viscosity, while the small particle will remain at the top as they lack the mass to travel through the more viscous layer, okay. Viscous layer is obviously the density, right? An average particle would migrate up to the middle portion. So after the centrifugation, the particle will be found in a series of zone or band placed according to the relative velocities of the particle, okay. So after separation, you will again get 3 or 4 bands, each band containing different type of particles depending on their similarities in density and most importantly size. So in red zonal centrifugation, you need to keep in your mind that in red zonal centrifugation, the column will produce the gradient, or the matrix forming substance will produce the gradient for you before centrifugation, okay. That is a very important line, okay. And when you are adding a high concentration medium, you have to put the tip of the pipette up to the bottom of the column without avoiding the interface between the layers, okay. And the last important thing, that as a prevention, or as a, what I should say, as an important thing you need to keep in your mind, that in case of red zonal centrifugation, the prepared gradient should be used as soon as possible to prevent the premature diffusion of the gradient layers, okay. So in case of red zonal centrifugation, we are separating particles on the basis of their size, okay. And another important formula that can come in exam, that is the molecular weight determination in case of red zonal centrifugation. So there the formula is m is equal to small f v by omega square r, where f is equal your frictional coefficient and v by omega square r is your sedimentation coefficient. And here m means the molecular mass in gram per mole, okay. That means that is their standard molecular mass, that is the 44 for in case of carbon dioxide, okay, not the 4 we have discussed. The 4 will be in case of small m, okay. So that is the idea of the red zonal centrifugation. In red zonal centrifugation, the important thing is that the column will prepare the gradient before centrifugation, and the 3 precautions you have to keep in your mind, that at high concentration media adding, you have to keep, or you have to insert your tip of the column at the bottom of the column, okay. The tip of the pipette should be at the bottom of the column without disturbing the different kind of layers, the interface between the layers, okay. And another important thing, after preparation of the gradient, we have to use it then and there, otherwise we cannot prevent the premature diffusion of the gradient layers, okay. That is a loss of us. And red zonal centrifugation separate particles on the basis of their molecular weight, okay. So that is the concept behind the red zonal centrifugation, okay. Now let us discuss about isopicnic centrifugation. So 2 things I want to mention that you need to keep in your mind, that isopicnic centrifugation differs from red zonal centrifugation in that in case of isopicnic centrifugation, the matrix forming substrate you are using will form the gradient after centrifugation. Okay, there will be a self generating gradient during centrifugation that will complete after the completion of the centrifugation. That is why you will get your gradient after centrifugation. That is the difference between isopicnic centrifugation and red zonal centrifugation. Okay, because in case of red zonal centrifugation we have seen that the gradients are forming before centrifugation and we are using that gradient to do our centrifugation job, but here we will have isopicnic gradient in isopicnic centrifugation after centrifugation. Okay, so isopicnic centrifugation is independent of time and it is depend on solely of Bowen density. Okay, that means the effective density of the macromolecule in the solution will control the isopicnic centrifugation. Okay, whenever a particular macromolecule's Bowen density match the particular environment's density, the molecule will stop. That is the concept of isopicnic centrifugation. Okay, there is nothing new. So the first goal of us will be to prepare the matrix. Okay, and another important requirement here, we need uniform mixture of sample. Okay, we will add those uniform mixture of sample. I have referring this as US in the mixture in the matrix forming substrate which result in the homogeneous mixture. Okay, that is the two important requirement. Matrix forming substance will be chosen in such a way that it will give you the gradient after centrifugation and you will use the uniform mixture of solution for your job. Okay, so after that, after the homogeneous mixture is formed, that is the sample and the medium, we will fix our tube with the centrifugal machine along with a balance. Then we will run the centrifugal machine for certain time, then we will get different type of distinct band that we have seen in case of red zonal centrifugation, but in case of isopicnic centrifugation this gradient was not there prior centrifugation. This is the result of centrifugation. Okay, and each of the gradient contain different layers. Okay, or different layers, or I should say different bands, and each of the band contain different type of particles in which each of the particle have same Bowen density. Okay, suppose let me choose a picture that I can use to explain you. Yes, okay, let's go back to this one. So in case of isopicnic centrifugation, the distinguishing idea is you will get this kind of band gradient, that means lowest density at the top and the highest density at the bottom only after centrifugation. Okay, and it will create different layers or band for you, and each of the band contain particles that are having same Bowen density. Okay, so suppose the Bowen density for granulocyte and erythrocyte is exactly equal to the environment that is in this point. Okay, so granulocyte or erythrocyte will stop here, phycol will be stop here. Same concept, phycol's Bowen density is exactly equal to the density in their medium. Mononuclear cells will stop here because mononuclear cells Bowen density is exactly equal to the condition that is here, and then plasma. Okay, and another important thing that is important, that in isopicnic centrifugation you do not get any kind of pellet. Okay, because isopicnic centrifugation is independent of time. No matter at what speed, at what amount of time you have run your tube, there will be no pellet at the bottom. That is the another important significant characteristics of the isopicnic centrifugation. So fourth thing, you will get your gradient after centrifugation, and it is performing the separation on the basis of their Bowen density mainly, and it is independent of time. And the last one is you will get no pellet at the bottom, no matter at how much speed and at what amount of time you have run your tube in the centrifuge. That what I have written here. At this point, the density of the macromolecule is equal to the solvent. This is an equilibrium precision. This is independent of time. By this method, the particle will never set even to the bottom of the tube, no matter how long the centrifugation time is. So, no pellet will be formed. Okay, and separation is on the basis of the density gradient, our Bowen density. Now, another important interesting topic, that is properties of a ideal density gradient medium. That we are talking about, that we are using a matrix forming substance, So what kind of properties that we need to keep in your mind during that matrix formation? So first thing is, the matrix should be easily autoclavable. It should be easily removable from our particles that we are separating. It must be cost effective. It should have sufficient solubility to provide the range of the density required. It should not be toxic, and it should not be metabolized by the cell, and it should not affect the biological activity of the sample. Okay, that means sample should be our density gradient medium should be inert for the sample, and it should be cost effective and autoclavable. That is the concept of isopicnic centrifugation, the concept of red zonal centrifugation, and importantly the properties of ideal density gradient medium. So again, density gradient centrifugation is nothing but centrifugal separation in a column. That column contain a density gradient. Okay, in that density gradient, the lowest density will be at the top and highest density will be at the bottom, and the intermediate density will be at the middle. So it have two parts, one is isopicnic centrifugation, another one is red zonal centrifugation. In case of red zonal centrifugation, the separation is on the basis of size and density, and red zonal centrifugation you will get your gradient before centrifugation, and in case of isopicnic centrifugation the separation is solely on the basis of their Bowen density, and in isopicnic centrifugation the gradient will be after centrifugation. In isopicnic centrifugation you do not get any kind of pellet, but in case of red zonal centrifugation you will get pellet, and in isopicnic centrifugation it is independent of time, and red zonal centrifugation is dependent of time. That is the difference between the two kind of density gradient centrifugation, isopicnic and our red zonal centrifugation. So we have discussed about the preparative centrifugation, where we are separating a particular type of molecule from a mixture. Analytical centrifugation, where we are analyzing the molecule. Fixed angle bucket rotor centrifugation, where we are holding our tube at 45-degree angle. That facilitates faster separation, no doubt about that, but it cannot ensure that all of the particle will slip down from the side where it have struck to the bottom. Okay, because here the direction of the force is exactly opposite to the position of the particles, and in case of swinging bucket rotor we are placing our tube horizontally, okay, during the movement, and this swinging bucket rotor ensure separation of the supernatant and deposited particle easily. Okay, and here luckily the direction of the force is exactly at the direction of our particles. RCF value, RCF is the comparative study depending on the type of rotor we have used and the speed at which we are rotating our sample. RCF is R omega square by G, omega is 2 pi rpm by 60 and G is 980. By placing all the formulas we can get a relationship between RCF to rpm. Sedimentation coefficient, that is the value of S Here Vedberg is important, that is the sedimentation coefficient of 10 to the power minus 13 second. Differential centrifugation, separation of subcellular component on the basis of their differences in sedimentation rate. Density gradient centrifugation. Density gradient centrifugation is divided into two parts: red zonal centrifugation, isopicnic centrifugation. Red zonal centrifugation provides the gradient before centrifugation, and isopicnic centrifugation provides the gradient after centrifugation. Red zonal centrifugation separates particles on the basis of their size and density, and isopicnic centrifugation separate particles on the basis of their Bowen density mainly. And now the last topic of today, that is ultracentrifugation. So ultracentrifugation, again it is nothing new. So if we are willing to undergo centrifugation where the sample is too small that along centrifugation cannot separate, so here we are using in such kind of cases ultracentrifugation. Okay, so ultracentrifugation can move at a speed of 60,000 rpm to 1,50,000 rpm. That separates more smaller molecule that cannot be separated by normal centrifugation. So ultracentrifugation is preferred for most facilitated laboratories and in more advanced operation. So here another thing, that ultracentrifugation can control sample in batches or in continuous flow system, and here we are using the refrigerator to control the heat that is generated by that intense amount of speed. Otherwise our cell can be, or what kind of biological molecule we are handling can be disrupted because of their intense heat. So principle is nothing new, principle is as same as we have discussed about the normal centrifugation, that is the sedimentation principle. That means denser particle will move faster than the less dense one. But here we are using the sedimentation force, that is why we are generating we are spinning the tube, because along gravitational force cannot going to solve our problem that we have discussed, and as it is a too smaller molecule, random thermal motion will also inhibit the sedimentation of those kind of particles. So we have to spin the tube at a very high rate or at a very high rpm, so that our this high centrifugal force will generated, that I can say in that kind of situation as ultracentrifugal force. This ultracentrifugal force will help gravitational force to sedimenting those kind of particles. So here the particles inside the tube are rotating about an axis, which result in the generation of a perpendicular force, that is called centrifugal force. Okay, so after that, so that is the idea. So centrifugal force will help larger and denser particle to settle fast, because larger molecule will move faster than the smaller one, and denser molecule will move outwards the periphery of the tube, whereas the less dense one are rotated towards the center of the tube. Okay, result in the sedimentation of the larger and denser particle. So ultracentrifugation can be divided into two types, that is analytical ultracentrifugation, another one is preparative ultracentrifugation. In analytical ultracentrifugation, we have detector system that detects the position of the particle and the spinning, that ultimately during live or real time, that means when the centrifugation is going on, that ultimately help us to detect the what is the sedimentation coefficient, and sedimentation coefficient in turn help us to find out various physical properties of the molecule. How? Sedimentation coefficient can tell us about the hydrodynamic property of the particle. Sedimentation coefficient can also characterizes the changes in size and density when we are changing the experimental condition. Okay, here I have mentioned here that macromolecules with changing experimental condition. how size and shape of the macromolecule changes with experimental condition, and the determination of the relative macromolecular weight with the help of analytical ultracentrifugation can be done with the help of sedimentation velocity approach or sedimentation equilibrium methodology. So three optical systems are available. One is our, so we have three kind of optical system. One is our fluorescence, absorbance and interference that will permit precise and exact location of the sedimentation in real time. Okay, and one of the example of this is clearance system. The CLN system will allow us to determine the particles position and importantly movement in centrifuge real time. That position will help us to determine the sedimentation coefficient, and sedimentation coefficient in turn help us to determine the physical properties. And analytical ultracentrifugation is commonly used for determination of properties of biomolecules. So AUC contains a detector. This detector help us to detect the location and spinning live during centrifugation. That help us to yield the sedimentation coefficient, and sedimentation coefficient in turn help us to determine hydrodynamic property. Then sedimentation coefficient can characterize the changes in size and shape during of a macromolecule with changing experimental condition. Then with the help of sedimentation velocity approach, sedimentation equilibrium methodology, we can determine whether what will be the relative molecular weight of a macromolecule. Then for that purpose we have three kind of optical system: absorbance, interference and fluorescence. This absorbance, interference, fluorescence help us to determine the precise sedimentation in the centrifuge real time. That help us to determine the what is the sedimentation coefficient. Fluorian optical system, for example. That is how analytical centrifugation help us to analyze a particular complex biological mixtures. Okay, such as determination of protein like biomolecules, protein, nucleic acid. Now in preparative ultracentrifugation, if you want to separate a mixture, okay, from, or you want to separate a particular type of molecule from a complex mixture, then you can use preparative ultracentrifugation. The exciting difference between preparative ultracentrifugation and analytical ultracentrifugation is that in case of preparative ultracentrifugation, the analysis will be going on after the centrifugation, not in real time when the centrifugation is going on. That is the difference between preparative ultracentrifugation and analytic ultracentrifugation. Preparative ultracentrifugation is often operated with density gradient centrifugation and differential centrifugation. So in density gradient centrifugation, that means our zonal centrifugation, our sucrose density gradient centrifugation, isopicnic centrifugation, in which particles are separated on the basis of their density, right? They will generate different layers or bands where each of the particles density is equal to the density of that particular environment, right? And in case of differential centrifugation, by increasing the speed of the centrifuge rotors and by increasing the time of the centrifugation, we are separating different molecules on the basis of their differences in sedimentation rate. And when we are doing all kind of things at a very high speed to separate more delicate particles, we can say them as preparative ultracentrifuge. So that is the idea. So what are the use? You can purify crude extract with the help of ultracentrifugation. You can pellet fraction of cells organelle like mitochondria, ribosome and even viruses with the help of preparative ultracentrifugation. Analytical ultracentrifugation will help you to determine various properties of biomolecules, and ultracentrifugation is also used for determination of densities of various macromolecules with the help of our PC technique, that is preparative ultracentrifugation. Sorry. So we have wrapped up the entire chapter of centrifugation, where we have first discussed about preparative centrifugation that separate a particular molecule from a complex mixture, then analytical centrifugation where we are analyzing the different particles of the mixture, then fixed angle centrifugation where we are holding the tube at 45-degree angle. It will ensure faster separation, but it cannot ensure that whether all of the particles are moving to the bottom or not, because in case of fixed angle centrifugation the substance will strike at the side of the tube, and this side is exactly the opposite side of the direction of the force. As a result, the separation will exactly be if they are slipped down or not. If they are slipped down, they will be at the bottom of the tube, otherwise they will remain. That means there is a chance of wastage. But in case of swimming bucket rotor, although the separation is not at first at in case of fixed angle, but there is no wastage in case of swinging bucket rotor, because here the direction of the force and the direction of the molecules is exactly the same. So relative centrifugal field R omega square by G, where we have to remember about omega is equal to 2 pi rpm 60 if we are calculating it in rad per second. That help us to find out what is the relationship between RCM and RPM. Sedimentation coefficient V by omega square R. Differential centrifugation, separating particles on the basis of their differences in sedimentation rate. And density gradient centrifugation, here are two parts. One is red zonal centrifugation, isopicnic centrifugation. In isopicnic centrifugation, density gradient is after the centrifugation, and in red zonal centrifugation, density gradient is before the centrifugation. In isopicnic centrifugation, it will be independent of time, and in case of red zonal centrifugation, it will be dependent of time. In red zonal centrifugation, separate particles on the basis of their size and density, and isopicnic centrifugation, separate particle on the basis of their Bowen density only. Then we have discussed about ultracentrifugation, where we have talked about AUC and PC. AUC will analyze the particle by analyzing the sedimentation coefficient live, and PC will separate or help you to pellet important fraction of cells. The difference between ultracentrifugation and centrifugation is very simple, that ultracentrifugation provide a faster and higher centrifugal force to separate more smaller molecules that centrifugation cannot. So that is the end of the lecture series of centrifugation.